Hello and welcome back. In the last video, we learned Newton method to solve nonlinear equations. In today's video, we will go through the MATLAB's process to code the exactly same method that we learned in the last video, how to code that to solve a nonlinear equation. So I have written a code in MATLAB Live Editor, and I will take you through that code step by step. So first consider the function that I have taken 4 of x cubed plus cosine of 2 times x. We assume that here x is in radians inside this cos function. So if you plot this function, it looks something like this. And we know that there is no way to solve this nonlinear function analytically. So we'll take the help of Newton method to solve this equation. So first things first, let's clear the environment for our code to run. So it's always good practice to clear your environment before running any new script, because sometimes you may have old variables of same names, and you never know that your script could take value from the old variables in the workspace and use that value in your code. That could result in incorrect values or incorrect outputs. So let's clear the environment by using clear, close, and CLC commands. And then we define our function. Here we have used a symbolic toolbox, and we use a sims function that creates symbolic variables. So here our symbolic variable is x, and we have defined function f of the same, it's the same form, 4 of x cubed plus cosine of 2x. Then the next step is to compute its derivative. So for derivative, we use this diff command in MATLAB that computes the derivative of function f with respect to x. So let's run these sections one by one. So here on our right hand side, we can see live output of this section, and so we can see that the derivative of 4x cubed plus 2x is 12x squared minus 2 sine 2x, which is of course correct. And analytically, if you see that when we take derivative, since they are in addition, so we take the derivative of each part separately. So derivative of 4x cubed will be 12x squared, and cosine of 2x will be minus 2 sine 2x. So next step is to convert these symbolic functions into MATLAB functions so that we are able to insert values in both the function and its derivative. So we have a command in MATLAB function that converts symbolic functions directly to MATLAB functions. So we do that here in this section block. So it's pretty simple. So let's run it. Yeah. So here we have a function with function handles x and in this form. So we have the function and its derivative in the form of MATLAB function now. So we can insert any value in these functions and get the output. So next is to initialize some important parameters that are needed to evaluate this Newton method. So we have a couple of things to declare. The first is the initial guess. Then is the tolerance or threshold that I discussed in my previous video, that we always need some kind of threshold in the iterative processes to stop the process whenever we get the result within the threshold. And just for is for the iterative method to see how many iterations it will run through. We have to define a certain threshold. So here we say that okay, we have a maximum of 100 thresholds, and if the function does not converge within these 100 iterations, then we can declare that we cannot solve this nonlinear function. So this is our kind of upper limit on the iterations. And finally, we have to initialize these variables, x and iteration with 0. Of course, it will start with something as 0, and our error is infinity. So just to recall how to find the next value when you have started your Newton method with some initial value x naught. So if you recall from previous video, we have this function x1 is equal to x naught minus f of x naught divided by f prime of x naught, where f prime is the derivative that we have computed earlier. So we have to compute this x1 and then x2 and then x3 and so on until we meet our criteria. So we have to iterate. So we are using while loop here, and the while loop is checking whether our error is greater than threshold or tolerance, and iteration is less than maximum number of iterations. So since here is an and, so it will check both of these conditions to meet before stopping this loop. And so we are computing f of x naught by this equation, and then f prime of x naught by using this equation, and then we compute x1 or x next by applying this formula. So it is coded as x next is equal to x minus f time divided by f prime. So we can find the error by computing the difference of x next with x. So that is done here in our next line. So based on the value of x, now in next iteration we will have x next as x, and we will perform the same step and keep on checking the this stop while condition or stopping criteria, whatever you call it. And once it's met, then we can simply print that convergence is reached. So let's run this section and see what happens. Sorry, I did not execute the previous section to run this section. Sorry. And yeah, so we see that our convergence is reached, and we have advanced to next section. And let's reach. So in the last section, we will find the root. That was the root, and how many iterations it took to compute this result. So let's run this one. Okay, so we have our root at like minus 0.5, and it took around 31 iterations to reach the root. And if you again revisit the plot, you will find that x y is axis is meeting. I mean, y at 0 is meeting x-axis somewhere at minus 0.5. So that is somehow verifying our results. So so what if we don't need that strict threshold, like 1 exponential minus 6 is very, very accurate, but maybe we don't need that accurate results. So what can we do? So we hope that in that case, the number of iterations should not be that large, or should not be 31, or maybe it should less than 31. So let's just play around with this code and see what happens when we have reduced this threshold or tolerance. So we are reducing this tolerance from 1 exponential minus 6 to, say, minus 2. So in that case, let's see what happens. So we have to rerun these sections to compute all the results from fresh. So we run this at advance, and then we move to the next section. And when we run this section, again, we see the code is convergence reached, and we run again. And see, now you notice that our root is slightly changed and number of iterations have reduced. So this is how you can reduce the load or burden on your system whenever the requirement of this accuracy is not that stringent in the case. So that's it. I hope now you have understood and you can implement this whole thing by yourself. So do let me know in the comment section and that how did it go. And if you have any problems, do mention that in the comment section. So thank you very much for watching, and see you next time with a new video. Take care. Bye.